supported by Patreon. Dear friends, thank you for supporting us on this platform. Stars seem to us to be eternal and ever-present wanderers of the universe, but this is just an illusion. In reality, they go through a series of metamorphoses, and their lives have a beginning and an ending. Born in the bizarre chaos of gas and dust clouds, stars burn brightly for millions and billions of years only to eventually perish in a dazzling flash. And today, we will follow this fantastic path together with many amazing stars. Our journey will begin in the middle of the mysterious Orion Nebula, a cradle for thousands of young stars. Then we will follow their evolution using the example of an amazing binary para. After that, we will embark on a long flight among the star systems surrounding the Sun, from newly formed stars to mature main-sequence stars. After that, we will make our way to the burning giant living out the last moments of its life, the titanic CW Leonis. And then we will fly past a celestial body that has already undergone a transformation from a bright star into a dark and mysterious object, a black hole. Here we will see how extremely strong gravity distorts and tears apart the very fabric of the universe, giving rise to amazing natural phenomena. Let's get ready, and we begin. Cosmo. First, there are stellar nurseries richly scattered across the galaxy, with some of them comparatively modest in size. Others stretch for tens and even hundreds of light years. These are vast nebulae made up of interstellar gas and dust being inexorably compressed by gravity forces. Most of these tremendous clouds are barely visible against the abyss of space, but some of them can be seen from the Earth with the naked eye. One of these structures is the Orion Nebula, located 1,344 light-years away from the Earth. It is the middle object in the so-called Sword of Orion, a clearly visible line produced by three relatively bright light sources. Due to its large size and comparative closeness to the Earth, the nebula has been attractive for scientists ever since the early days of astronomy. It is hardly surprising, therefore, that this great structure is one of the best-studied space objects. It was the Hubble Orbital Space Telescope that beamed back first images of the Orion Nebula back in 1993, where the rich diversity of its colors can be appreciated. Most of the material was of a reddish or bluish-purple hue, while unusual bright green lines of some peripheral areas were revealed by spectral analysis. This phenomenon perplexed scientists for a long time, as the observed radiation did not demonstrate any chemical element known at the time. There was even a hypothesis that was put forward about there being a hypothetical element nebulum argued to be not present on our planet, but allegedly amply scattered across clouds and space. However, with the advancement of science, it turned out that the light was emitted by extremely rarefied and deionized oxygen. This discovery accounted not only for the bizarre illumination of many nebulae, including our Sun. There are currently not less than 3,000 stars discovered in the Orion Nebula to date, as well as giant clouds of interstellar gas and a great number of protowars. All this amazing diversity of space objects is concentrated in an area of around 23 light-years in diameter, all of them continuously and elaborately interacting with each other. The overall mass of the material concentrated here is around 10,000 solar masses. Looking at the Orion Nebula closer, we will notice several clearly defined areas. The most outstanding of them is Trapezium, also known as Theta 1 Orion. It's an open star cluster about 300,000 years of age, made up of 8 main components. Some of them are binary stars, others have no companions. The brightest and most noticeable of the trapezium stars are 4 stellar systems designated by letters of the Latin alphabet. Located close to each other, they lie within an area about 1.5 light-years in diameter. Each of these objects' mass is within 15 to 40 solar masses, which means that these stars are quite young and hot. Theta 1 Orion C is the most massive as well as the brightest star in both the trapezium cluster and actually the entire nebula. It is a white and blue main sequence star with a mass roughly 40 solar masses whose radius is 8 times that of the Sun. The object's surface temperature is approximately 45,000 Kelvin and its luminosity about 250,000 times higher than that of the Sun. The radiation of Theta 1 Orion C illumines virtually all the nebula around it, but there is hardly any interstellar gas in its immediate vicinity. This is the case due to the fact it is typical for objects of this class to experience exceptionally powerful stellar wind that scatters rarefied material far off. Having traveled a few light-years away from trapezium, we will see another remarkable system, which is Theta 2 Orion. It is made up of 3 gravitationally bound stars located close to the so-called Orion bar, an extensive feature of hot gas emitting bright light. It was impossible to study this area for a long time on account of dense clouds of dust, and thanks to the James Webb Telescope, more detailed images of this region have been beamed back to us. The first component of Theta 2 Orionis is just slightly less massive and not as luminous as the trapezium's biggest star. As for its surface temperature, it measures about 35,000 Kelvin. The second component of the system is 15 times as massive as the Sun and 12,000 times as bright. The third component is as heavy as 5 solar masses, and its temperature almost reaches 14,000 Kelvin. However, it wasn't just bright stars that caught the researchers' attention. James Webb's infrared cameras allowed it to detect previously unseen objects hidden deep within the clouds of gas and dust. Thanks to the telescope, about 180 so-called proplids have been discovered at the heart of the Orion Nebula. These are dense, dark protoplanetary disks surrounding stars that are still in the process of formation. One of these is Orion 294-606, a young protoar about 1 million years old surrounded by a gas and dust disk, about 300 astronomical units in diameter. Thanks to its being a John to Earth, we can observe its structure and size. It is expected to hit the main sequence phase in a few million years, and it will be accompanied by a system of several exoplanets and possibly their satellites. The night sky of these future celestial bodies must be a truly fantastic sight. Just imagine a multicolored luminous veil with a glow of a multitude of close and bright stars far more numerous than those seen from the Earth coming through. And now and then tremendous swirls of glowing gas cover half the sky, turning the night into translucent twilight. If we fly a little further and examine the wider region, we see that the bulk of the nebula is filled with scattered gas. The central part of the cloud is filled with highly ionized hydrogen, which actively absorbs high-energy stellar radiation. The temperature of this gas can reach 10,000 Kelvin, but it falls sharply towards the edge of the region. Temperature and pressure contrasts as well as the collision of stellar wind streams set material in space in motion, creating tremendous currents and vortices. According to calculations, some of them can reach speeds of up to 50 km per s, and their size can be greater than the solar system. Also, in some areas of the nebula, thin strands stretching for several light-years have been detected, consisting of relatively cool molecular hydrogen without mixtures of methane, ethane, and water. Further out, we will see that the central region of the Orion Nebula is enveloped in a vast cloud of cooler, denser gas. The cloud of bright stars and the luminescence of ionized hydrogen intricately intertwine here, creating a beautiful multicolored curtain of light. Hidden behind it are hundreds of space objects invisible in the optical range. But the infrared cameras of today's telescopes allow us to see through the veil of interstellar matter. By combining data from different sources, astronomers have discovered about 700 protoars at different stages of evolution within this region. Their concentration is noticeably lower than in the central part of the nebula due to the lower degree of gravitational compression of the interstellar gas. The absolute majority of these objects are very young by space standards and are still in the process of formation. According to modern concepts of stellar evolution, new stars form during gradual gravitational compression of large clouds of interstellar gas. Typically, as a result of this process, giant nebula split up into a number of closely grouped gravity centers, which soon turn into protoars. Such clusters are called stellar nurseries, or more scientifically, regions of star formation. At a certain point, the internal pressure of the compressed gas compensates for the gravitational forces, bringing the protoar to a state of temporary equilibrium. The remaining material swirls into a giant vortex disk, with some of it gradually absorbed by the future star and the rest of it, by contrast, expelled far beyond the boundaries of the nascent system. The growing magnetic field of the young star also plays its part as ionized particles accelerate through its field lines and then rapidly escape from the vicinity of the object. It has been calculated that such flows can reach speeds of up to several hundred km/s. As they collide with the gas clouds surrounding them, they create large-scale vortices and hemispheres called Hering-Haro objects. In the process, part of the kinetic energy dissipates into light and heat, giving these bizarre structures different colors. In addition, the ultra-fast motion affects the surrounding material, spreading shock waves across it, which incidentally are also captured by telescopes. Since stellar nurseries contain many closely spaced protoars, each producing several gas emissions, It is not surprising that her big Haro objects exhibit an amazing variety of shapes and colors, clearly being essentially the result of a major cosmic collision. They're highly unstable and variable. Her big Haro objects rapidly change color and shape and typically disperse completely over several tens of thousands of years. During this time they cover between 1 and 3 light-years on an escape trajectory from their parent stars. About 400 such objects have been discovered so far, with their total number within the Milky Way estimated to be about 150,000. Perhaps one of the varieties of this awe-inspiring natural phenomenon is the bullets, hundreds of astronomical units in diameter also detected in the Orion Nebula. Moving at incredible speeds, they easily pierce thinner hydrogen clouds, creating far-flung shockwaves in them. According to spectral analysis, the frontal parts of these objects contain atoms of iron that glow in the infrared. The bullets are estimated to be about 1,000 years old, and their origin is still a mystery. They supposedly originated from some catastrophic event. Moving on, we will soon find that the Orion Nebula is part of a much larger cosmic structure called the Orion Cloud. It stretches for hundreds of light-years, accounting for virtually the entire constellation of Orion in the Earth's night sky. This is where the well-known Horsehead Nebula is located. Remarkable for its bizarre shape, it is a dense dust cloud about 3.5 light-years in diameter, clearly visible against a background of a contrasting scarlet glow. Also close to the Orion Nebula, there is an impressive cosmic structure called the Barnard's Loop. This emission nebula, about 300 light-years in size, came into being about 3 million years ago after a series of consecutive explosions of mutually closed supernova. After the shock-compressed gas jets mixed together, they produced a gigantic curved nebula, and the glow of several young stars gathered in an open cluster made it reddish in hue. For all its beauty, the Orion Nebula is a fragile and unstable object by the universe's standards. Stellar winds and pressure of light from many young stars as well as gas emissions and turbulent vortices constantly disperse its material in the surrounding space. The nebula has already lost about 60% of its original material, and in about 100,000 years it will be stripped of its remnants. In place of the shiny multicolored cloud, there will remain an open star cluster similar to the Pleiades. For a time, the young stars forming it will move together, but eventually each will find its separate way through the vast expanse of the boundless galaxy around. According to today's concepts, the life of any star is determined almost exclusively by its mass. With a star's mass being less than 8 solar masses having completed several evolutionary stages, it eventually turns into a white dwarf. It is assumed that after billions of years it will lose the rest of its energy and transform into a hypothetical object called a black dwarf. This path is destined for more than 99% of the universe's stars, including our Sun. If the mass of a star exceeds 8 solar masses, however, its evolution follows a different path, eventually resulting in a supernova explosion. The outer shells of the star are scattered in the surrounding space, forming a scattered gas nebula. At the center of the system there remains a super-compact and extremely dense object, the former stellar core. Its fate also depends entirely on its mass. If it is too great, the core of the dead star will not be able to resist the inexorable gravity and will inevitably shrink into a black hole. However, there is another way. In the case where the mass of the stellar remnant is within the range of 1.4 to 2.2 solar masses, a neutron star is formed. Gravitational forces in its interior destroy atomic nuclei, forming a super-dense neutron matter with rather bizarre physical properties. For a number of reasons, neutron stars are extremely difficult to observe and study. Firstly, celestial bodies of this class are extremely rare. According to calculations, there is only one such object per 1,000 ordinary stars. Secondly, they are very compact and practically do not emit light in the optical range. Therefore, before the advent of X-ray telescopes, it was impossible to spot these objects. Not surprisingly, the first neutron star was discovered only in 1967, several decades after the theoretical justification of their existence. This is largely due to an unusual phenomenon associated with the law of momentum conservation. Thanks to this effect, most neutron stars have a very high rotational speed, and the interaction of their magnetic and electric fields generates powerful bursts of radiation repeated with a very clear periodicity. Such objects are called pulsars, and they make up the majority of neutron stars discovered so far. Their pulses are effectively detected by X-ray telescopes, even at distances of thousands of light-years. In total, more than 3,200 neutron stars have been discovered so far, and about 90% of them are single objects. The rest are part of binary and multiple systems. Most often the companion of these cosmic bodies is a red giant or a main sequence star, but in isolated cases another neutron star. This happens when two similar stars synchronously approach the end of their life cycle, and the explosion of one of them triggers the collapse of the second. Because of the loss of energy during the transformation, the remnants of stellar nuclei closely converge, which causes their mutual velocity to grow to enormous values. And according to today's concepts, this is how the amazing system called PSRJ 737 3039 music was formed. It is located at a distance of about 4,500 light-year from Earth, and is quite unique, being made up of even two pulsars located very close to each other. The first of them is 34% more massive than the Sun, has an incredible speed of its proper rotation. Every second the object completes 44 revolutions around its axis. The second pulsar is a little smaller and slower. Its mass is 1.25 of that of the Sun, and the rotation period is 2.77 seconds. If we want to take a closer look at these objects, we will see that their size is extremely small by space standards. Either component of the system is no more than a couple of dozen km in diameter. As for their mass, it is actually comparable to that of most known stars. Due to these factors, the density of the matter that the pulsars are made up of is extremely high, and in order to understand this question we need to look into their interior. The use of mathematical modeling techniques combined with the theory of neutron star structure allows us to learn even things not immediately visible. The outermost layer of objects of this class is the atmosphere. Incidentally, however, for neutron stars, this concept differs significantly from the familiar sphere of gas a planet is enveloped in, like that of Venus or the Earth. For both components of the system we're looking at now, this layer is no more than a few mm thick. This situation is typical for the absolute majority of neutron stars. But the youngest and hottest objects of this class may have an atmosphere of several dozen cm. It's made up of plasma, highly ionized remnants of stellar matter. Most of it is hydrogen and helium atoms, but heavier elements are also to be found. The next layer is the outer crust, which can be several hundred mm thick. The gravity in this region is not strong enough to overcome the electrostatic repulsion between electrons and protons, but it is enough to destroy the usual structure of matter. Elementary particles are all jumbled together but still retain their internal integrity. Several powerful forces are pulling on the outer crust at once, such as gravity, magnetic field, electrostatic repulsion, and centrifugal inertia. This combination places the surface of neutron stars under constant mechanical stress. Occasionally it builds up to a point where starquakes occur, titanic deformations of the surface of the cosmic object. As a result, therefore, mountains a few millimeters high and cracks up to a centimeter wide. These numbers do seem insignificant, but at extremely high gravity, a centum-high mountain is comparable to Olympus in the conditions of Mars. If we go still lower, we will see that this layer has no clear boundaries, and goes several km deep into the neutron star. As we dive into its interior, the pressure gradually increases, causing more and more electrons to be pushed into the atomic nuclei, initiating a reaction with protons. As a result, a neutron is formed, as well as a highly evasive particle called neutrino, which almost immediately leaves the interior of the celestial body, taking excess energy with it. In turn, beneath the inner crust, there lies the outer core, which consists entirely of neutron matter. This amazing substance is a multitude of tightly compressed neutrons, and its density is 10 to 15 times higher than that of the atomic nucleus. For example, our planet compressed to the same degree would have a radius of only 150 m, and a cubic cm of its volume would contain several billion tons of neutron matter. In both components of the system we're looking at, the outer core continues as far as the center of the object. Incidentally, particularly large neutron stars should also have an inner core. According to today's concepts, its structure is still a subject of scientific debate. According to one hypothesis, the pressure in the center of massive stars can be so great that it is capable of destroying even neutrons, forming a hypothetical quark matter. Such an object is called a quark star. Other assumptions allow for the formation of hyperonic or con nuclei consisting of some bizarre matter with highly unusual properties. However, all these amazing structures are still within the domain of hypothesis. and to prove or disprove their existence is not yet possible. If we look at the system as a whole, we will discover several surprising and intriguing facts. First of all, we can notice that according to calculations, the pulsars in this system are moving rapidly around a common mass center along moderately elongated and very compact orbits. Observations show that the average distance between the components is only 800,000 kilometers, which is almost half the diameter of the Sun. Because of this small distance, the speed of mutual motion of both objects is very high. It exceeds 300 kilometers per s. So, the pulsars make a complete revolution around a common mass center in just 2.45 hours. Such rapid motion causes a number of unusual phenomena due to the effects accounted for by the theory of relativity. For example, observations show that at the moment of maximum convergence of the pulsars, the period of proper rotation of each of them temporarily increases by 38 microseconds, after which it returns to the previous values. Even though this effect cannot be explained from the point of view of classical physics, the theory of relativity predicted it long before its practical detection. This anomaly is associated with the relativistic time dilation, which becomes the strongest exactly at the moment of maximum convergence of objects. Another phenomenon that stands out occurs during mutual eclipses and is associated with an anomalous red shift detected in the spectrum of one of the pulsars. The point is that the gravity of the component closer to us interferes with the signal from the distant object passing by it. Because of this, the radiation loses energy and its wavelength increases. It is also known that the orbits of these celestial bodies are affected by their interaction. This is reflected in the fact that the point of their maximum proximity, called the period, is constantly shifting. This phenomenon is called relativistic shift and has long been known to astronomers. It is usually recorded when studying fast celestial bodies. For example, Mercury's orbit shifts by 43 arcs-seconds every 100 years. As for the period of the binary pulsar, it shifts 140,000 times more strongly. Within a year, it deviates from its previous position by as much as 17 degrees. Thus, PSRJ 737-3039 has the highest relativistic shift among all stellar systems known so far. If we leave the dry figures for a moment and think about hypothetical planets that may be hiding in this amazing system, their existence seems rather unlikely but still possible. Some objects far from the center did have a chance to survive the crushing double explosion of the supernova, while others may have formed later. It is still harder to answer this question due to the fact that none of the widespread methods of searching for other planets are effective for exploring such systems. In any case, we cannot speak of the viability of the hypothetical celestial bodies of this system. The freezing cold and deadly radiation make them extremely inhospitable places. Observations show that this binary pulsar is constantly generating gravitational waves, causing the distance between its components to steadily decrease by 7 mm every day. This phenomenon occurs in all physical multiple star systems, but is usually too faint to be measured with any degree of certainty. This tells us that in about 85 million years, the pulsars will merge together to form a black hole. The tremendous cataclysm will be the source of super-powerful gravitational waves that will travel through the entire Milky Way and reach other galaxies far beyond it, and the flash accompanying the merger may briefly become one of the brightest stars in the Earth's sky. In any case, the echoes of this devastating explosion will eventually fade without a trace in the infinity of the universe. By galactic standards, the area of space on the outer edge of the solar system is considered to be sparsely populated by both stars and other space objects. Still, approximately 50 stellar systems are known to be located within the radius of 15 light-years from the Earth. Some of them are single stars while others contain 2 components and more, which is why the total number of stars in this area reaches 65. Many of them have exoplanets and protoplanetary disks, made up of gas and dust where celestial body formation processes are still in progress. In order to analyze this great variety, we'll have to map out the environments. As we slowly recede from our home planet, we will cover dozens of light-years of space and visit quite a few remote worlds. It is time to set out to the stars. Having traveled 6 light-years away from the Sun, we will reach our first stop, a small red dwarf designation GJ 699, also known as Barnard's star. It is remarkable for its incredible travel speed across the sky, and also for the fact that it's capable of crossing the lunar disk in the course of 180 years. This is due not only to its close proximity to us but also to its great proper motion. Barnard's star is moving towards the solar system at a speed of slightly over 100 kilometers per s, and is going to become our closest star in about 10,000 years. By then, the distance between Barnard's star and our Sun will be just 3.8 light-years. But the red dwarf is so dim that it will not be visible even at such a small distance, and it will be possible to observe it only through optical devices. The star's mass is just 17% that of the Sun, and its radius is 6 times as small as that of our star. Just like all red dwarfs, Barnard's star is quite cool with a surface temperature just 3,134 Kelvin, or slightly under 2,900 degrees C. With these characteristics taken into account, it isn't surprising that the object's luminosity is 2,300 times lower than that of our parent star. In 2018, the results of a 20-year observation of the star's proper motion were published, which may provide evidence for the presence of an exoplanet nearby. The calculations show it to be a cold super-Earth with a mass of not less than 3.2 times that of the Earth. The planet named GJ 699b is located about 4 astronomical units from the center of the system and takes 233 days to complete a full orbit around its parent star. Unfortunately, the exoplanet follows an orbit that does not lie between the Earth and its parent star, so it's hardly feasible to carry out spectral analysis of the object. Still, mathematical modeling may give us some insights into what it's like. As Barnard's star is very dim, its planetary companion receives 50 times less energy than does the Earth from the Sun. That is why the temperature on the celestial body's surface is extremely low, just 105 Kelvin or 168 degrees C below zero. However, it cannot be ruled out that tidal disturbances or radioactive decay may have released enough energy in the planet's interior to form a warm subsurface ocean. If that is the case, the potential life in its depths would have had ample time to gradually develop. For among the known stars, Barnard's star appears to be one of the oldest. According to estimates, its age is over 10 billion years, which is only a fraction of the expected lifespan of a star. As it is located quite close and is moving in a favorable direction, Barnard's star is one of the highest priority objects for a potential interstellar flight. Time will show if spacecraft launched from Earth will ever reach it. Meanwhile, on the other side of the Sun, there lies the almost exact opposite of the dim red dwarf. Of course, we're talking about Sirius, the brightest star in the night sky, which is 8.6 light-years away from our planet. From Earth, the star appears to be a single light source, but close inspection revealed that it is not a single object but a binary star. The two components of the system are currently at their maximum distance from each other, about 30 astronomical units. The main star, also called Sirius A, is a bright blue and white star with a mass 2 times that of the Sun. At the same time, it is about 70% larger in diameter, and its surface temperature reaches 10,000 Kelvin. Because of this, Sirius A emits 25 times more energy than our Sun. The second object, known as Sirius B, is barely visible against the background of its bright and massive companion. It is a white dwarf, with a radius of about 6,000 kilometers, and a mass very close to that of the Sun. Like all stars of this type, its surface temperature is extremely high, reaching 25,000 Kelvin. However, due to its small size, this white dwarf is about 1,000 times dimmer than its stellar companion. After long and persistent research, no signs of planets have been found in the vicinity of Sirius. The reason for this may lie in the comparatively young age of the stellar system, or else the special position of the ecliptic plane. Because of this, the hypothetical exoplanets do not pass between the light source and the Earth, and therefore cannot be detected by the transit method. Another hypothesis claims that Sirius B exhausted its stellar fuel supply roughly 120 million years ago and transformed into a red giant. Soon afterwards, it shed its outer layers, turning into a compact and very hot white dwarf. As a result, the protoplanetary gas and dust disk, enveloping the young stellar system at the time, was destroyed by this explosion, its remnants scattered into the space around, denying the forming planets any chance of survival. Currently, both components of the system are moving around a common mass center in moderately elongated orbits, completing one every 50 years. Over the next 60,000 years, Sirius will gradually approach Earth, becoming brighter and more visible in the night sky. The minimum distance between us will be about 7½ light-years, after which the system will start to slowly drift away from us. Things will go on like this for about another 660 million years, after which Sirius A will meet the same fate as its companion. For a brief moment, a massive flare will boost its luminosity by a factor of thousands, but within a few months, the star will fade completely, vanishing from the sky forever, leaving the vicinity of Sirius permeated by lethal ultraviolet radiation and stellar wind. We will perform a maneuver near the solar system to reach a small star 14 light-years from the Earth. It is designated differently in different catalogs, and one of its names is Wolf 1061. The star is a red dwarf with a radius of about 30% that of the Sun. Its mass is about 4 times smaller than that of our star, and its surface temperature is 3,272 Kelvin or about 3,000 degrees C. Like all objects in its class, Wolf 1061 is extremely dim. Its luminosity is only 0.14% that of the Sun, so the star is not visible to the naked eye from Earth. However, this red dwarf has one of the most abundant and diverse planetary environments of any stellar system near us. As many as 3 exoplanets have been discovered in its vicinity, all of them rocky and similar in composition to Earth. But still, conditions on each of the 3 celestial bodies differ considerably. The first and closest exoplanet to the parent star is called Wolf 1061b. It is located 0.038 astronomical units from the center of the system and completes a full orbit around it roughly every 5 days. The object has a mass in the range of 1 1/2 to 2 Earths, and a radius 20% greater than that of our planet. It is likely that the celestial body is tidally locked and faces its star with one side at all times. For this reason, the temperature on the day side of the planet is extremely high, and the flares and stellar winds of the star so close to it virtually rule out any chance of there being an atmosphere. All these factors make the exoplanets completely unsuitable for the genesis and support of life. The second object in the system, Wolf 1061c, is located 0.089 astronomical units from its star and completes full orbit around it roughly every 18 days.